And coming up next. Coming up next is Paolo Papotti, who will present his work on explainable fact-checking with probabilistic answer set programming.
All right. Thank you for the introduction. So, good afternoon, everybody. It is joined to work with my students Naser and Mohammed. We are from Eurocom in France, and our collaborator in ASU in the US, Professor Lee. So, we already had a very good presentation earlier about the motivation for computational fact-checking, so I'm not going to claim again that is something important, and of course we're not trying to replace the human here, but we are trying to assist the humans with tools that will make their life easier and the job faster. But we see also that this adoption of computational fact-checking methods is something that is still not there. And one of the reasons we argue is because we don't have a clear, transparent explanation of why a claim, why a fact is considered correct or wrong. So our overall goal is to make fact-checking transparent by providing explanations. So when I talk about explanations, the idea is that if we have a claim, such as Elon Musk is the founder of Chevrolet, our system will not only say that it's false, but it will give also some explanation saying that Chevrolet was founded in 1911, and Elon Musk was born in 1971. So this is our argument to say there is some logical explanation to tell you why this is false. Okay? So in this case, the evidence is quite straightforward, but there are some other cases that are more subtle. For example, if I have a textual claim stating that this guy, Michael White, he got a degree from UT Austin, in this case, it is harder to check, and in fact, our system will use multiple small pieces of evidence to say that it's false. Specifically, our system says that he believes that it's false because he already works for UT Austin, and in academia, especially in North America, if you are working in a place, it's unlikely that you got your degree there. And also, he already has 2 degrees from 2 other universities. So usually people don't get so many degrees. Okay? So those are weaker signals, but when you combine them, they provide some insight at the things that you have to consider to understand why this is false. Okay? So how do we do this? Getting a bit more precise, basically our system for now is limited to claims that are expressed as one fact that looks like a predicate stating that the alma mater for Michael is UT Austin. Okay? This triple is expressing the relationship between a subject and an object. And then we take as input also a noisy and incomplete knowledge graph. This is basically a database expressed as a graph that contains semantic information. So here, in this little example, you see Paris that has the type city, and it's in relationship with the Eiffel Tower and the Louvre because they are both located there, and the Louvre is a museum, etc., etc. And you see that these types and relationships, those are the key of our ability to explain the facts, as it will become clear in a moment. These knowledge bases, there are many of them. We rely a lot on DBpedia and Wikidata, and there are many, many others that are open in the public. They are general purpose, but there are also many knowledge bases that are created in the enterprise, in institutions, and they are more domain specific. And our system can take any of them, of course, as input. And to make it more clear, a knowledge graph that is based on RDF, it looks like this. We have triples, and they express this relationship between entities, such as Barack Obama and Michelle Obama. They are in the spouse relationship. But also we can have entities and values, such as the birth date of Barack Obama is 1961. Okay, so we say that we have subject, predicate, and object. As I mentioned, there are many of those, and I like to show this table because it gives a feeling of how they are structured. You can see that they have thousands of different types and thousands of different relations. Okay, This is very important because it means that they're very expressive. They have a lot of things that they can describe with some semantic, okay? And in terms of instances, they go in the millions, okay? So now we saw something about the input. Let me explain better how we obtain the output. So we will say that this is false, and what we will expose to the user is that we have some evidence. The first piece of evidence is that in the knowledge base or somewhere else, as I will show in a moment, we found that it's working in a different place, and he already got degrees from 2 different venues, okay? So the big question is, how do we know that those are meaningful pieces of evidence, right? So the fact is that we rely on a set of rules that are defined over the knowledge graph. Now, don't get intimidated by the logic here. Basically, those are just saying that if you have an alma mater from a certain place, and you have another alma mater for a different place from the first one, it's likely that there is a contradiction, like with a 10% probability. Okay, those are some statistics that we compute, of course, from the knowledge graph. And if you are working in a university and you got the alma mater from the same university, it's likely with some support that you are, that is a contradiction again. Okay, so the question is, how do we get those? If you're familiar with knowledge graph, you know that these rules are not there. They're simply not there, and there are thousands and thousands of entities and different predicates, so we cannot manually add them. Okay? So the answer here is in a tool that we developed last year. We published in ACDE, and basically is a system to mine these rules from the knowledge graph. And here we see the example with a slightly more complex rule. The atoms, those are the predicates from the knowledge base. The universal variables that you see are the ones that are going to be replaced by the values. And here this is saying that if you were born after a company is founded, you cannot be the founder. Or, by being more precise, basically what we're doing is that we are assigning the values from the subject and object that are in the founder. So Musk get assigned to X, Chevrolet get assigned to Y, and then you see there is all this assignment of the different pieces. So what he found is that the evidence coming from the knowledge base together with the claim that I'm checking, all together there is a contradiction. Okay, so at least one triple in this set must be incorrect. So our system will take this piece of information with a confidence of 0.9 to take the decision. Okay? So we call them negative rules because they identify inconsistencies. And of course, we mine them at scale over all the knowledge bases. So for example, here we have examples from Wikidata and Iago, I believe, where we take the fact that we discover the fact that we cannot have a president that is not born in the US, if you are in the US, or you cannot be married to your child. Okay, that is with 0.9 because actually there are some errors in the knowledge base of people that are married to their children, so the rule is reflecting also the quality. But we will see why we are robust to these errors. Okay, we also discovered positive rules. Those are a different kind of patterns where we basically handle the missing information in the knowledge base. If you have two people with, if a child is reported as being the child of two people, they are likely to be married with a certain probability. So, for example, Michelle and Barack Obama, they have a child in common, so we can derive that they're likely to be married. We call them positive rules, and of course we can mine them from the knowledge graphs. Okay, we have a simple one here that is describing the symmetric relationship between notable work and creator in Wikidata, and another pattern over family from Iago. Okay, so there's a little glitch here, but I hope that you can still get it. So I'm ready to present the architecture of the system, just to give you a feeling of how this works. So you already know what is a claim. We call it C in this picture. So we have the triple that Musk is reported as the founder of Chevrolet somewhere, and we want to check this. So tree is part of the input together with the knowledge graph. We saw them. So once we get these two pieces, we are able to derive our assessment on the right. So you see that we are able to see that it is false with a certain explanation E. Okay? We also have a module that is going over the web to find more evidence. So this can be replaced with other documents, with Elasticsearch or a database, anything that can provide more evidence at the extensional level, which means at the level of the triples that are missing in the knowledge base. So sorry, there is a little confusion here. So basically, here I'm discussing the rule discovery module at the top left, inside the architecture. So this module is in charge of discovering the rules from the knowledge base and as the evidence, the pieces of the knowledge base that are useful to assess the claim. So here there is the example with the rule that you saw earlier. So this module is in charge of discovering these rules, and indeed it is a rule coming from the knowledge graph, giving it a confidence, 0.9, and then to identify the pieces of the knowledge base that are important to assess the claim. Okay, so the claim is founder, e-mask, Chev at the bottom, C, and then he will identify that in order to use this rule, he must also use founding year and birth year of these people. And then once we have this, we feed our reasoner that takes all the rules that are coming from the system with the evidence, and there is a probabilistic extension of answer set program with the concept of weighted rules, which is crucial for us because we have rules that are approximate with some confidence, and basically it is going to take the decision over the claim to say that the claim is true or false, and then we can collect the rules that have been used to produce the explanation. The big challenge is also, as I mentioned earlier, that some of the claims need evidence that is not in the knowledge base. So what we do is that we look at the rules that are partially instantiated. Like in this example, I'm assuming that there is no information about Elon Musk and his birth year. So we will be in a setting like this where we have the founding year, we have the claim, but we cannot check it because there is a piece that is missing. So in this case, what we do is that we take a state-of-the-art tool and we just ask it, can you find for us the birth year of this guy from the web? And we will get a number, and as you can see, now we also have 0.6, which is the trust that the tool is giving to this piece of evidence. So the reasoner is not only taking care of the approximate rules, but also of the approximate facts, because they come with some confidence value. Okay, so I forgot to mention that the previous model is called MAP. That is basically the approximate version of the reasoner, because as you may know, when you do this reasoning, it can be very slow if you have many rules and many entities. So that is the standard method, and then we have the extended method with the web evidence. Okay, so let me tell you quickly some results to give you a feeling on how this works. So we took DBpedia, 300 predicates, 300 facts, positive and negative from each for 4 predicates. So we had 2,400 claims. We removed the true claims from the knowledge graph. Thank you. We removed the true claims from the knowledge graph so that we can actually test them. Otherwise, it will be too easy. And then we use precision recall and F-measure. It is a technical detail because we have some cases where our reasoner will say that it's uncertain because some information is missing. So we use a F-measure in the table that is coming. And we also use 3 baselines. So the text miner is the system that I showed earlier that is going over the web by itself. Then we have a link prediction method over the knowledge graph. There is a standard algorithm based on machine learning that take the claim, and it will see if this claim can fit into the graph, and it will say yes or no. And then finally, we have the rules applied in considering them are the rules, which means we don't use the confidence of the rule. So there is no reasoner here. Okay? So those are some of the state-of-the-art methods for for this problem. And you can see the 4 predicates: alma mater, that place, spouse, and vice president. And our methods are at the bottom. You see that we have, in 3 cases, the best performance. Of course, when we do the map with W, which is the one using the information from the web, what happens is that the recall goes up because we can check more claims, but we make more mistakes because in some cases this evidence is just not correct. And for one case, we have another method that does better because we could not find enough evidence to trigger the rules. Okay, so there is a lot of room for improvement here, but the most important argument for us is that we are comparable, but we can also provide this kind of explanation. Okay, so for every claim, we have a set of arguments that will tell you this is false because I found this kind of evidence that contradict the original claim. So I'm going to stop here, and basically I hope that I give you some insight about the fact that we can get this semantic explanation by using reference data. I'm a database person, and I'm here to advocate the use of structured data like knowledge bases and databases to make fact-checking stronger. And looking forward, we are trying to extend this to more complex claims. That is the major limitation for now. We want to use natural language generation to produce nicer explanation. And finally, looking forward, we would like to change this from yet another fact-checking tool to something that is more focused on the explanation of the decisions, something that you can use as a module on top of other systems that can be coming from other groups, but our idea is that we can sit on top and try to explain their output based on our techniques. And I will stop here. Thank you.
I have time for a couple of questions.
Hi, thank you very much for your talk. My question is about the nature of the explanations that you can support at the moment. And from the description of the rule generation that you gave me, it feels like that whilst, yes, you can point to relations and entities in the knowledge graph that would prove, for lack of a better word, let's say, with some probability that this is correct or incorrect. There's really no explanation about why those rules were chosen, other than they happen to be frequent in the knowledge graph.
Very good point. So, yes.
So, yeah, I was wondering if...
I mean, you're touching more on the work on the mining, which is definitely a key ingredient here. So, for the sake of time, I'm not giving many details about how we mine the rules, right? But that's our algorithm that is based on some ideas in the mining that is able to identify rules that are the best rules. And our magic is that we don't consider only positive facts that are in the knowledge graph, but we have also a sophisticated method to create negative facts. So the way that it works is that when you do the rule generation, you use for the positive rules, you use the knowledge graph as evidence and the negative examples to validate these hypotheses that are coming from the positive. The cool thing is that when you discover negative rules, you use these guys to create hypotheses and these guys to validate. You see? So we can talk more about this if you like.
Yeah, great talk, thank you. I really like this type of work and looking at knowledge bases to fact check. I'm wondering if you have a sense of how much the given knowledge bases that we have freely available or even in companies, would cover the kinds of claims that people would make that are wrong in the real world. Like a lot of the examples, and that's natural, and I do that too, they're sort of artificial because maybe people wouldn't really lie about those. They maybe make mistakes, but it isn't the kind of thing that people actually sort of lie about intentionally.
I completely agree. So let me tell you, my answer is that I'm using this as a prototype to prove that it's possible to get the explanations. But you see that even in this little prototype, we had to go to the web to get some of the evidence that is not in the knowledge base. So looking forward, that's why I think that it's more valuable to focus on the fact that we can get these rules and patterns that are semantically valid somewhere, and then for the instances, for the extensional level to do the substitution of the variables, basically, we can go to other sources. So now we are using the knowledge base and the web, but we can use databases so that it can surface, from other sources, not only from the knowledge base. I totally agree that it will be limited, and that's also our experience. Okay, thank you for the questions. And
yeah,
I think
thanks. Sorry,
close.
we've run out of time, so apologize. But thanks again for the
Thank you.
And just a quick, yes, while Tracy Farrell is taking the stage to present her work on understanding the role of human values in the spread of misinformation, a quick announcement. There was a laptop that went missing during the break. If you have a laptop that you've somehow found and is not yours, please, I don't know, if you found a laptop like just in your pocket that you shouldn't be there, like, I don't know. Just please keep an eye out and please return to the registration desk. Color of the laptop? Brown. Yes, thanks a lot. Sorry, it's a notebook.
It's a notebook.
Oh, sorry, sorry, my brain is a bit, sorry, I was wrong. It's a notebook and not an electronic one. It's actually one that you use with a pen. Sorry, apologies. So it's a notebook that you write on with your pen.